Hi everyone, my name is Katelyn and I'm going to be covering the stress-strain relationship. I chose this topic because this relationship is highly relevant in footwear development in addition to orthopedics, or the branch of medicine that deals with the musculoskeletal system. In Module 1, Lecture 4, the stress-strain relationship is used to define the mechanical properties of material and their response to an imposed load or force. So the slope or load deformation curve on the graph indicates how stiff the material is. The two variables on the graph include stress, which is the y-axis, and strain, which is the x-axis. Stress is measured in pascals or newtons per meter squared and represents the applied force divided by the total area where the force is applied. And strain is unitless because it is determined by dividing the change in length by the original length when the force is actually being applied. It represents the total deformation of the material when it's undergoing stress. Different areas of the graph indicate the various responses of a material as greater force or stress is applied. The load deformation curve can be different depending on the stiffness and ability for a material to withstand stress. So the elastic region represents the ability of a material to return to its original length and shape after the stress is applied. And at a certain point when the stress becomes too great for the material to withstand, it will hit the yield point and become plastic. So once a material has become plastic and undergone this amount of stress, it will not return to its original shape. Failure indicates when the material would undergo an amount of stress that would cause it to break. The elastic modulus indicated by E is the rise over run of the slope in the elastic region, and this is used to determine the stiffness of the material. So now that I've talked about the stress-strain relationship, how does this concept actually apply to the human body in biomechanics? So when an elastic material is under stress, the ability of the material to spring back to its original shape is considered stored mechanical energy. Most materials, like a shoe, will have a linear relationship with stress and strain, but the human body does not actually behave in the same way. The body is not purely elastic, it's actually viscoelastic. So this means that the tendons, bones, ligaments, and muscles will respond differently to stress depending on the direction and duration of the load, as well as the positioning of the body. For example, the length and tension of the gastrocnemius and the Achilles tendon, whenever we are in plantar flexion or dorsiflexion, will elicit different mechanical properties throughout the load deformation curve. The femur bone pictured is undergoing axial loading, and the red portion of the bone is where the stress is centralized. So when we break a bone and our bone surpasses failure, the break can change depending on the speed and direction and intensity of the applied stress. The way stress is applied to our bones is going to dictate how a fracture occurs. Since bone is viscoelastic, the speed and length of the load will cause the bone to respond differently. It will also respond differently based on the direction of the load or stress. Bone is an anisotropic material, meaning that it will behave differently based on the load direction. For example, wood is also an anisotropic material, so it is stronger along the grain than across it. Bone is stronger when loads are applied in the longitudinal direction, and weaker when it is applied transversely over the bone surface. These images shown came from teambone.com, a website created by an orthopedics laboratory in Utah. Force or stress can be applied in several different ways, including compression, tension, shear, and torsional loading, where the material is twisted. Compression will compact the material, tension will pull the material, and shear pushes the material eccentrically, according to the website. The way in which the force is applied can allow someone to predict the type of fracture that will occur. So an example from the Utah laboratory states that a femur will be very strong when loaded in compression, but will reach failure with much less force in torsion and is very weak in shear. Materials aside from the human body can be isotropic, which means its load deformation curve will react the same with all types of applied force. This type of data is important for collecting information on the mechanical properties of various materials, including properties like strength, elasticity, and overall resilience to stress. So when choosing materials and designs to build equipment, such as a running shoe, they need to consider how the shoe will change the impact force on the body, as well as how the shoe material can withstand repeated stress. It is also important when developing implants and determining their biomechanical properties. Implant material should have an elasticity that is similar to bone and high tensile, compressive, and shear strength to prevent a bone fracture.